Okay, in this video, we're going to talk about nuclear chemistry, and specifically radioactivity. Let's start by reviewing some atomic notation. Now, we can represent a given nucleus or a given atom with the symbol of the element, as well as the number of protons, called atomic number, and protons plus neutrons, or mass number. So remember, the nucleus is composed of two nucleons, as we call them, protons and neutrons. Nucleons just as the collective term there for these nuclear particles. And the number of the protons is the atomic number. Okay, so if you wanted to specify these with sort of symbols, that number 6 here is the number of protons, which we have the symbol of P plus for. And this upper superscript of 12 for this given atom of carbon is the mass number, which is the number of protons plus the number of neutrons. If you subtract 12 and 6, mass number minus atomic number, you get the number of neutrons, 6. And any given atom of carbon will always have an atomic number of 6. So it's really enough to just write 12 and carbon, because it's implied if it's an atom of carbon, it has 6 protons. That's what makes it carbon. Now, you will see different isotopes of carbon, right? You can have a carbon 12, you can have carbon 13, you can have carbon 14. These are all different isotopes, meaning the number of protons is the same. They're all 6, and I don't have to write those 6s there. You know it because it's a C atom or carbon. All the same number of protons, but carbon 12 has 6 neutrons. Carbon 13 has 7. And carbon 14 has 8. Right, so these are all isotopes. Carbon 12 is most of the carbon in the universe, 99% or so. Carbon 13 is about 1%, and carbon 14 is really tiny amounts, but that's actually what we use in carbon dating, which we'll talk about in the next lecture. But for now, just understand this atomic notation and isotopes. Sometimes isotopes are written out like this, so you could have carbon-12, or here we're showing uranium-234, uranium-235, and uranium-238. Right? So in atomic notation, those just look like this. And these are 3 different isotopes of uranium. There's more than 3, but these are the 3 principal ones. Uranium-238 is, I think, 99%. Uranium-235 is like 1%. And uranium-234 is really tiny amounts. And actually, I just want to highlight here that uranium-235 is the only naturally occurring element that can sustain a nuclear chain reaction. And we'll talk about that in a future lecture as well, but that's really important. So I just wanted to highlight here as we introduce this concept of isotopes and atomic notation that we're already somewhat familiar with, but refreshing here. Now, let's talk about what can happen inside an atom's nucleus in nuclear chemistry, and specifically radioactivity. So some nuclei, not all, but some have excess energy in them. And just like if you think about an atom, here's the nucleus, and in the simple sort of Bohr model, there's various orbits, and an electron can relax down and emit radiation or excess energy when it does that. Well, nuclei are kind of similar in the following sense, that they can have excess energy and relax and emit radiation. So this emission of radiation, when nuclei change and relax, okay, we call these nuclei then radioactive. And the precise nuclei that do this, or groups of nuclei that do this, are called radionuclides. So atoms with nuclei that have excess energy that are prone to emitting radiation, those precise nuclei are called radionuclides. And the process they're undergoing is radioactivity when they emit this radiation. Now, there's several ways radionuclides can decay or relax into a different nuclide. So the premise here is that one atom is actually going to change into another atom by changing its number of, for example, protons in the nucleus once it emits this radiation, right? So carbon might be changing into something else, okay, like beryllium, right? A whole different type of atom. Now, we use nuclear equations to show how these reactions occur. So these are going to look just like chemical reactions. So we could have a chemical reaction like H2 plus Cl2 goes to 2 HCl, right? That's a chemical reaction. It is balanced. There's the same number of hydrogens and chlorines on both sides. In nuclear chemistry, we have equations as well, but they're written to express the mass numbers and atomic numbers. And we have to ensure that just like chemical reactions, things balance. So nuclear equations are meant to show how an atom is changing its nucleus. So here on the left, we're starting with an atom of uranium-238. Uranium is defined to have 92 protons. It can have some excess energy in its nucleus it wants to get rid of, and it does so by emitting something called an alpha particle. And we'll talk more about that exact type of radiation, one of the 5 types we'll talk about here in the coming slides. But for now, let's just examine this atom of uranium that's sitting there. It has some extra energy in its nucleus, and it gets rid of that energy by emitting this alpha particle. And with it, its nucleus no longer has 92 protons, it now has 90 protons because 2 of those protons left in the form of an alpha particle. 2 neutrons also left as part of that alpha particle because this alpha particle has a mass number of 4, an atomic number of 2, so that's 2 protons and 2 neutrons. So we denote this alpha particle with this helium nucleus here. And the numbers of, let me use a different color here, atomic number and mass number must balance on each side. So you want to always be adding up your atomic numbers and making sure they're balancing, as well as your mass numbers. So 90 plus 2 is 92, 234 plus 4 is 238. And here we're showing a uranium atom changing into a thorium atom. Okay, so the same way we balance sort of chemical reactions with the types of atoms on each side and the number of those atoms on each side, we're making sure we're balancing the atomic number and mass number here. Now, let's get more into the specifics of the different types of radioactivity we can have, starting with this first one we just briefly alluded to, alpha decay. Alpha decay is the loss of an alpha particle. And so you can have this atom, like uranium-238, with extra energy in its nucleus, and it can relax by emitting 2 protons and 2 neutrons at the same time as one discrete particle. And that particle is essentially a helium atom without the electrons, right? Because a helium atom is a nucleus of 2 protons and 2 electrons with a couple electrons orbiting it. And so if you didn't have those electrons, that is just a nucleus of 2 protons and 2 neutrons. Okay, so this alpha particle, sometimes you'll see it written as just the symbol alpha. But usually in these nuclear equations like this, you're going to see it referred to as helium-4 as if it's just another atom. And it's sort of implied here that it's just an alpha particle, no electrons involved there. So this is a very small, very stable thing, and is a good thing to emit for a nucleus trying to get rid of some extra energy. Notice this equation still balances, as we just alluded to, 92 on each side and 238 on each side. So this is one way that a nucleus can get rid of energy. Emit an alpha particle. 2 protons, 2 neutrons at the same time. A second way a nucleus can emit energy or radioactively decay is through beta decay. So we had alpha decay, now we have beta decay. And here we're emitting a beta particle. And really this is just an electron. So you'll see it written like this or like this. But in either case, it is just an electron. And it's a very, very high-speed electron emitted by the nucleus. So it's not that you have some electron living in the nucleus. No, you have a nucleus here, you have some electrons orbiting out here. This nucleus has some extra energy it's trying to get rid of, and it all of a sudden emits an electron out of nowhere. It creates it and emits it. And that electron has such a high energy, it just goes off and leaves the atom. It's not captured by the atom. It doesn't stay in some orbital or something. It is just born out of the nucleus like that and goes zinging off into space. Now, how does that happen? Well, really this extra energy here in the nucleus is when there's too many neutrons in the nucleus, and that is the source of instability. And so the nucleus wants to change one of its neutrons into a proton. That would make it more stable. And so to conserve charge, it has to make an adjustment. If it's turning something neutral into something positive, then it's going to have to be emitting something negative, and that is the electron here. So sometimes you'll see this written in the nuclear equation as an electron on the right side like this, or as I said before, a beta particle, but these mean the same thing. And you're always going to see it on the right side of the equation here if it's beta decay. This atom of iodine has too many neutrons. It's going to change a neutron into the proton, and as soon as it does that, it at the same time creates this electron out of thin air to conserve charge here, and the electron goes zinging off into space. So notice that the mass number is not changing. Why? Because the total number of nucleons is staying the same. It's changing a neutron into a proton. So there's still the same total number of neutrons and protons, but the atomic number has changed. It's gone up by 1. Now, are atomic numbers and mass numbers still balanced? Because we're showing here that this electron is leaving, and we're specifying that this electron, right, effectively accounts for this neutron creating a proton here. And so we can still add the right side up. 54 minus 1 is 53. 131 plus 0 is 131. Those mathematics still work. So this is beta decay, emission of a beta particle, also known as an electron. And you'll see it always for beta decay appear on the right side of this nuclear equation. So we have alpha decay, we have beta decay, and then we also have gamma emission. Not gamma decay, but gamma emission. And this is a way for a nucleus that has too much energy just to get rid of that extra energy without creating some particle. Okay? And much the same way that an electron can relax down and emit light and radiation, right? A nucleus can relax and emit light as well. So this gamma emission is just a really high energy form of radiation. It is like light, right? Radiation, just like when an electron relaxes, it can emit light. A nucleus relaxing can emit light. And we call that light gamma emission, okay? And the loss of a gamma particle or gamma ray. Right? In other words, a photon or light. Right? So this nucleus relaxes and emits a photon. Now, this gamma particle or photon is going to be symbolized in nuclear equations like this with the symbol gamma and a mass number and atomic number of 0, because it's just light. It's not changing the number of nucleons, right? It's not an electron. It's not really doing anything. It's just getting rid of this spare energy. So no change in atomic number or mass number. And this is often going to be part of some other radioactivity processes, right? So maybe this alpha decay also gets rid of some extra energy with some gamma radiation, right? So this might be happening, okay, at the same time as something else. Sometimes it's just there for accounting purposes to make sure energy is not created nor destroyed, okay? But it is a type of radiation and radioactivity. Sometimes they're shown in nuclear equations, sometimes they aren't, but it's just one we want to be aware of. Usually we don't write it in these nuclear equations. As I've shown here, there maybe is gamma radiation also happening, okay? But it's not really explicitly shown always. So that's the third kind of radioactivity: alpha decay, beta decay, gamma emission. Now, we can also have positron emission. This is the opposite process of beta decay. Remember, beta decay we said was a nucleus that had too many neutrons and wants to change one into a proton to conserve charge. It also has to emit an electron. Well, here, the nucleus is unstable because it has too many protons. Okay? And here, we want a proton to be changed into a neutron in this particular nucleus. Okay? And so to conserve charge in this process, we need a different kind of particle that is not going to change the mass number, because we're changing one nucleon into another nucleon, not changing the total mass number, but it is changing the charge. And so to conserve charge here, we have this +1, and we call this a positron and use the symbol E, but +1. So kind of like an electron, we might refer to as E negative, or like this, if it's a beta particle or an electron. We are referring to this positron as E +1. And it is essentially an anti-electron. It has the same mass as an electron, but the opposite charge. That is what a positron is. And so this is just like beta decay, where the electron was created by neutron to proton. Here, a positron is created by proton to neutron. And this is positron emission. Mass number and atomic number are still going to be conserved. So 6 on the left, 5 + 1, 6 on the right, 11 on the left, 11 on the right. You'll perhaps sometimes see this written as beta plus, right? Just to sort of have symmetry with our beta decay, where we were emitting an electron. You could have positron, where it's beta plus instead. So sometimes it'll be written as that, but most of the time it's going to look like this for your positron. The final type of radioactivity we're going to discuss is electron capture. And this one is different than all the others in the sense that something is written on the left side of the nuclear reaction, right? The particle here that is being involved is appearing as a reactant, right? All of these others, the positron is on the right, gamma emissions on the right usually, beta decay is on the right, our alpha particle is on the right. And so in this radioactivity or radioactive process, electron capture, the particle is a reactant. And here's what's happening in this atom. Here you are involving one of the electrons in this atom. Okay, it is unstable. It wants to neutralize one of its protons and change it into a neutron. And it can do that by absorbing one of the electrons from its electron cloud. So here the process is you have some proton in the nucleus. It is neutralizing one of its own electrons and changing that proton into a neutron. This is electron capture. The nucleus is capturing one of its own electrons. Don't confuse it with beta decay, because this looks like a beta particle, right? But really our beta particles are going to be appearing as products here, right? This is what's emitted. This is beta decay when it's a loss of a beta particle that's going shooting off into space. Yes, it's an electron, but more specifically, it's a beta particle that's being created. Here, we are capturing one of our own existing electrons. This is not a beta particle because it is an electron that exists as an electron in our electron cloud that our nucleus is absorbing. Okay, so the nucleus absorbs this electron from its own cloud, neutralizes its proton, okay, and by doing so, one of its protons changes into a neutron. So again, the mass number is not going to change. One nucleon changing into another, so 81 on each side. But here, my atomic number is going to go down by 1 because the proton has been neutralized. So 37 minus 1 equals 36. Now, for energy conservation, you're pretty much always going to also have a gamma ray produced here. But again, this is not always specified, although maybe it is good practice for specifically electron capture to specify this gamma ray here, because it's always going to be produced as part of this electron capture process. So those are the 5 types of radioactivity I wanted to discuss in this video. We had alpha emission, and so an alpha particle symbolized by helium nucleus, or the symbol alpha. We had beta, symbolized by an electron. We had positron, symbolized like a anti-electron. We had gamma radiation, symbolized by gamma with 0 and 0. And we also had this last one, electron capture, involving an electron, but this time as a reactant. Okay, here's some other symbols we've used for neutron, proton, electron, but that really encompasses the 5 different types of radioactivity we're primarily concerned with in nuclear chemistry. Up next, we'll talk about radioactive decay using first-order kinetics and carbon dating. We'll also talk about how you can have nuclear energy and fission and fusion and those sorts of things as well. But that'll do it for this lecture. See you next time.